All right. Now we'll talk about gravity inside the Earth, or really any other planet, or maybe if you're going inside of a star or something like that. Now, the one thing to kind of point out about gravity is we can fairly easily calculate the force due to gravity if we're near the Earth's surface, or really near any planet's surface, and that force is just mass times acceleration of gravity. That's not so bad. We can also calculate force due to gravities at distances that are getting far away from the Earth's surface, and that's Newton's law of gravity. Force equals negative g m1 m2, where m1 is the mass of the planet, m2 is the mass of the object, and r is the distance between the center of the planet and the center of the object. My question would be, what if we start drilling a hole deep into the Earth? Maybe I want to drill a hole from here to the other side of the world. I'm going to go down into the Earth. What happens to the gravitational force as I go down into the Earth? Does it get bigger because I'm getting closer and closer to the surface of the Earth? Does it stay the same, or does it get smaller for some reason? Let's actually figure that out and see what would actually occur. So, let's say we're inside the Earth and we're at this point where this green box is, at a radius r from the center of the Earth. The cool thing about the force of gravity, if we take Newton's law of gravity, and let's say we break it up and look at your mass and the mass of every little rock inside of the Earth, and look at the gravitational attraction from all those objects. As you can see, we could set up an integral to do that, assuming the mass of the Earth is uniform, which may or may not be true. But what you actually end up with when you do that math is that if you draw a shell or a circle, or I guess a spherical shell in this case would be the better, at the radius of the Earth, or at the radius that you are away from the center of the Earth, all the mass that's outside of that shell causes a net gravitation attraction of 0. The reason for that, you can think of the mass that's above you is pulling you up because you're attracted, and that happens to cancel out for the mass that's below you. If you actually work the math and set up an integral to show what is the gravitational attraction for every bit of mass outside of the shell, you end up with 0. It's actually pretty cool because what this suggests is the only mass that is important is the mass that's closer to the center of the Earth than you are. Any mass that's inside the shell that we've defined. And so really the force due to gravity, we could define it as g, the mass inside, times your mass divided by r squared. So let's see if we can figure out something about the mass inside. Let's make the assumption that mass is uniformly distributed throughout the volume of the Earth. This probably is not true, but let's just say for the sake of argument that it is true. What that means is that we can define the volume density, which I'm going to use rho to talk about the density, mass divided by volume. Well, the volume of the Earth, the last time I checked, the way to measure the volume of a sphere is 4/3 pi r cubed. And so I do mass of the Earth divided by 4/3 pi r cubed, where r, e, is the radius of the Earth. And the density, if density is uniform, that number should also equal the mass inside of my sphere divided by the volume of the shell that I've created. That's the second term over here. So this is really the density for the whole Earth, the density for the stuff inside of me. What this allows me to do is calculate a function for the mass inside, and then it's mass of the Earth times r cubed, how far am I away from the center of the Earth, divided by the radius of the Earth cubed. Basically the ratio of how much of the Earth, or how close am I to the center of the Earth compared to the size of the Earth itself, is really the important ratio here. Now if I plug that in for m inside, what I end up with is a function that looks like this. G, mass of the Earth times my mass, divided by r cubed, or r, radius of the Earth cubed, times my radius. What this would suggest is, the closer and closer I get to the center of the Earth, guess what? The smaller and smaller gravitational mass gets, and then it's linear. That's kind of cool if we really think about it. So what I did was I took and said, what if I had a 10,000 kilogram mass and I wanted to figure out what is the gravitational attraction from the center of the Earth to a distance, I think I picked like the International Space Station or something like that. And what you find is that until you get to the surface of the Earth, which I've put in the black line here, here's the surface of the Earth, you get this nice linear function related to r. Well, once you get past the center of the Earth, what actually ends up happening is your m inside just becomes mass of the Earth. So when we get beyond the mass of the Earth, all the mass inside is just the mass of the Earth, and so you end up with just normal Newton's law of gravity, which is where you get this function here that goes on and on forever. And so if we want to look at gravitational attraction from the Earth, the place where you have the greatest gravitational attraction to the Earth happens to be on the surface of the Earth. If you start to dig deep into the Earth, gravity decreases linearly. If you start to get farther away from the Earth, gravity decreases by a factor of r squared. So that's kind of some cool things. We'll probably do some problems dealing this when we look at simple harmonic motion and look at the what if I drilled a hole through the Earth and dropped a mass into it, what would happen? It's actually a pretty cool problem if we actually think about it. We can actually then describe what's going to happen in that system.